By the end of the 19th century, physics stood at a strange crossroads. On the surface, it appeared to be a nearly complete science. The laws of motion, formulated by Isaac Newton, had successfully explained the movement of planets, projectiles, and machines for more than 2 centuries. James Clerk Maxwell's equations had unified electricity, magnetism, and light into a single, elegant theory, revealing that light itself was an electromagnetic wave. Thermodynamics had clarified the principles governing heat, energy, and work. Many leading physicists believed that the fundamental laws of nature were essentially known, and that future progress would consist mainly of refining measurements to greater precision. Yet beneath this confidence lay a growing sense of unease, as certain experimental results stubbornly refused to fit within the classical framework. One of the most troubling signs of crisis emerged from the study of thermal radiation. Physicists investigated how objects emit electromagnetic radiation when heated, a phenomenon known as blackbody radiation. A blackbody is an idealized object that absorbs all incoming radiation and emits energy solely based on its temperature. Experiments carefully measured how much energy a blackbody emitted at different wavelengths for various temperatures. These results were precise and repeatable, making them an ideal testing ground for physical theories. Classical physics attempted to explain blackbody radiation using well-established principles from thermodynamics and electromagnetism. However, when physicists applied these ideas, they encountered a severe contradiction. Classical theory predicted that as the wavelength of radiation became shorter, the emitted energy should increase without limit. This led to what later became known as the ultraviolet catastrophe, a theoretical prediction that hot objects should release infinite energy at very short wavelengths. Such a result was clearly absurd and directly contradicted experimental observations, which showed that radiation intensity rose to a peak and then declined at shorter wavelengths. This failure was not a minor technical problem. It struck at the heart of classical physics. The equations involved were logically sound and derived from principles that had been tested countless times. Yet when applied to blackbody radiation, they produced results that did not match reality. The inability to reconcile theory with experiment suggested that some deeply held assumptions about energy, matter, or radiation were fundamentally flawed. Another crack in classical physics appeared in the study of atomic structure. According to classical electromagnetism, electrons orbiting a nucleus should continuously emit radiation as they accelerate, losing energy and spiraling inward until the atom collapses. This prediction implied that atoms were inherently unstable. However, atoms clearly existed and maintained stable structures. Classical theory could not explain why matter did not simply collapse in on itself, nor could it account for the discrete spectral lines observed when atoms emitted or absorbed light. The nature of light itself also posed problems. Throughout the 19th century, light had been successfully described as a wave, explaining phenomena such as interference and diffraction. However, certain experiments hinted at particle-like behavior that wave theory could not fully explain. These inconsistencies suggested that the classical picture of light was incomplete, even though no alternative framework yet existed. Thermodynamics, while powerful, also raised conceptual difficulties. The second law of thermodynamics introduced irreversibility into physical processes, stating that entropy tends to increase over time. This seemed at odds with the time-reversible laws of classical mechanics, which made no distinction between past and future. Reconciling irreversible macroscopic behavior with reversible microscopic laws remained an unresolved puzzle and added to the sense that the classical world lacked internal coherence. Despite these growing problems, many physicists remained optimistic. They believed that small modifications or clever mathematical adjustments would resolve the discrepancies. Few imagined that the crisis demanded a radical revision of fundamental concepts. The prevailing attitude was that nature must ultimately conform to classical principles, and any deviations were temporary misunderstandings. However, as experimental techniques improved, the gaps between theory and observation became impossible to ignore. Precision measurements increasingly highlighted failures in classical predictions rather than eliminating them. The Blackbody radiation problem, in particular, resisted all attempts at explanation within classical physics. This persistent failure forced physicists to confront the possibility that energy might not behave as a continuous quantity, a notion deeply ingrained in classical thinking. The crisis at the end of the 19th century was therefore not marked by chaos or confusion, but by a quiet tension between confidence and contradiction. Physics had achieved extraordinary success, yet its most trusted theories could not explain some of the simplest and most fundamental observations about nature. The discipline stood on the brink of transformation, even though few recognized it at the time. This intellectual environment set the stage for a revolutionary shift. When Max Planck introduced the idea that energy is exchanged in discrete units, he was responding directly to the failure of classical physics to explain Blackbody radiation. His proposal did not merely fix a single problem. It exposed the limits of the classical world view itself. The crisis of the late 19th century thus became the gateway to a new understanding of nature, one that would soon evolve into quantum theory and forever change the foundations of physics. Blackbody radiation refers to the electromagnetic radiation emitted by an idealized object called a blackbody, which absorbs all incoming radiation and reflects none. Such an object emits radiation solely as a function of its temperature, not its material composition or surface properties. Although a perfect blackbody does not exist in nature, many real objects approximate this behavior closely enough to be studied experimentally. By the late 19th century, blackbody radiation had become one of the most important testing grounds for physical theories, because its behavior could be measured with great precision and appeared to follow universal laws. When a blackbody is heated, it emits radiation across a wide range of wavelengths. At lower temperatures, most of the radiation is emitted at longer wavelengths, such as infrared. As the temperature increases, the total amount of emitted energy increases, and the peak of the radiation spectrum shifts toward shorter wavelengths, eventually entering the visible range and beyond. This explains why heated objects glow red at first, and then become brighter and whiter as their temperature rises. Experimentalists carefully measured how the intensity of radiation varied with wavelength for different temperatures, producing detailed curves that any successful theory had to explain. Classical physics attempted to account for blackbody radiation using the well-established principles of thermodynamics and electromagnetism. A common classical model imagined radiation inside a cavity with perfectly absorbing walls. The electromagnetic radiation inside this cavity was treated as standing waves, similar to vibrations on a stretched string. According to classical statistical mechanics, each possible mode of vibration should carry an average amount of energy proportional to temperature. This assumption, known as the equipartition theorem, worked well for many physical systems and was considered a cornerstone of classical theory. When physicists applied the equipartition theorem to the electromagnetic waves inside a blackbody cavity, they obtained a mathematical formula for the energy distribution of radiation. At long wavelengths, This classical prediction matched experimental results quite well. However, as the wavelength decreased, the theory predicted that the energy density should increase without limit. In other words, classical physics implied that a blackbody should emit an enormous, even infinite, amount of energy at very short wavelengths, particularly in the ultraviolet region of the spectrum. This absurd prediction became known as the ultraviolet catastrophe. The term captures the severity of the problem. According to classical theory, the energy output of a heated object should blow up catastrophically at high frequencies. If this were true, everyday objects would release vast amounts of ultraviolet radiation, making the physical world unrecognizable and unstable. Experiments clearly showed that this did not happen. Instead, the radiation intensity rose to a maximum at a certain wavelength and then rapidly declined at shorter wavelengths. The ultraviolet catastrophe was not a small discrepancy that could be dismissed as experimental error. The disagreement between theory and observation was dramatic and undeniable. Classical equations, derived from principles that had been spectacularly successful elsewhere, failed completely in this context. The problem was particularly troubling because blackbody radiation involved fundamental concepts: energy, temperature, and electromagnetic waves. If classical physics could not explain such a basic phenomenon, its claim to completeness was seriously undermined. Physicists initially hoped that the problem could be solved by refining classical assumptions or introducing corrective factors. Various empirical formulas were proposed that fit experimental data well, but these formulas lacked a solid theoretical foundation. They described what was observed without explaining why it happened. The deeper issue remained unresolved. Why did energy emission drop off at high frequencies instead of increasing indefinitely? At the heart of the ultraviolet catastrophe was a classical assumption that energy is continuous. Classical physics allowed energy to be divided into arbitrarily small amounts and distributed smoothly among all possible modes of vibration. This assumption worked well for macroscopic systems, but proved disastrous when applied to electromagnetic radiation at very short wavelengths. The infinite number of high-frequency modes meant that energy could be spread endlessly, leading to the predicted divergence. The resolution of this crisis came from an unexpected and radical idea. In 1900, Max Planck proposed that energy exchange between matter and radiation does not occur continuously, but in discrete units. He suggested that each mode of radiation could only absorb or emit energy in fixed amounts proportional to its frequency. This proposal introduced a new fundamental constant, now called the Planck constant, which set the scale for these energy quanta. Planck's assumption had a dramatic effect on the radiation formula. By restricting how energy could be distributed among high-frequency modes, it naturally suppressed the contribution of short wavelengths. As a result, the predicted radiation curve matched experimental observations perfectly, including the sharp decline at ultraviolet frequencies. The ultraviolet catastrophe vanished, not because the mathematics was adjusted, but because a foundational assumption about energy was changed. It is important to note that Planck himself did not initially view his idea as a revolutionary statement about nature. He considered it a mathematical trick, a way to force theory into agreement with experiment. Nevertheless, the implications were profound. The idea that energy comes in discrete packets contradicted the classical view of a smooth, continuous universe, and opened the door to a completely new way of thinking about physical reality. The ultraviolet catastrophe thus played a crucial role in the birth of quantum theory. It exposed the limitations of classical physics and demonstrated that long-standing principles could fail under certain conditions. What began as a technical problem in thermal radiation became evidence that nature behaves differently at small scales than classical intuition suggested. In retrospect, Blackbody radiation and the ultraviolet catastrophe mark a turning point in the history of science. They show how careful experiments can challenge even the most trusted theories and force radical change. The failure of classical physics to explain Blackbody radiation did not signal the end of physics, but rather the beginning of a deeper and more accurate understanding of the universe, one built on quantum ideas that continue to shape modern science and technology. Blackbody radiation refers to the electromagnetic radiation emitted by an ideal object that absorbs all incoming radiation and reflects none. Such an object, called a blackbody, emits radiation purely as a function of its temperature. Although no perfect blackbody exists in nature, many physical systems closely approximate this behavior, making blackbody radiation a powerful and universal phenomenon to study. By the late 19th century, understanding blackbody radiation had become one of the central challenges in physics because it revealed deep inconsistencies within classical theory. When any object is heated, it emits radiation across a broad range of wavelengths. At relatively low temperatures, most of this radiation lies in the infrared region and is invisible to the human eye. As the temperature increases, the object begins to glow red, then orange, yellow, and eventually white, indicating that radiation is being emitted across the visible spectrum and beyond. Careful experiments showed that the distribution of this radiation follows a precise pattern. For a given temperature, the intensity rises with decreasing wavelength, reaches a peak, and then falls off sharply at shorter wavelengths. Physicists in the 19th century attempted to explain this behavior using classical physics, particularly electromagnetism and thermodynamics. A common theoretical model involved radiation trapped inside a cavity with perfectly absorbing walls. The radiation inside this cavity was treated as standing electromagnetic waves with different possible wavelengths and frequencies. Classical statistical mechanics was then applied to determine how energy should be distributed among these waves. A key classical assumption was the equipartition theorem, which stated that energy should be shared equally among all available degrees of freedom. Applied to electromagnetic radiation, this meant that each possible wave mode inside the cavity should carry an average energy proportional to the temperature. When this assumption was used to calculate the energy distribution of blackbody radiation, it produced a mathematical formula that worked well at long wavelengths. In the infrared and microwave regions, classical predictions closely matched experimental data. However, the same formula led to a disastrous prediction at short wavelengths. As the wavelength decreased and the frequency increased, the number of possible wave modes grew rapidly. According to classical theory, each of these modes carried energy, so the total energy at high frequencies should increase without bound. This implied that a blackbody would emit an infinite amount of energy in the ultraviolet region of the spectrum. This prediction was clearly unphysical and contradicted experimental evidence. Measurements showed that radiation intensity does not increase indefinitely at short wavelengths. Instead, it drops off rapidly beyond a certain point. The classical result, which predicted infinite ultraviolet radiation, became known as the ultraviolet catastrophe. The word catastrophe was used deliberately because the failure was not subtle or minor. It was a complete breakdown of theory in a domain where it should have applied. The ultraviolet catastrophe posed a serious threat to classical physics. The equations involved were derived from well-tested principles, and there were no obvious mathematical errors. The problem lay deeper, in the assumptions about how energy behaves. Classical physics treated energy as a continuous quantity, divisible into arbitrarily small amounts. This assumption had worked extremely well for macroscopic systems, but when applied to radiation at very short wavelengths, it led to nonsense. Physicists initially tried to resolve the issue without abandoning classical ideas. Several empirical formulas were proposed that fit experimental data accurately across all wavelengths. These formulas were mathematically successful, but lacked physical justification. They described what happened, but did not explain why it happened. The core question remained unanswered: why does nature suppress high-frequency radiation instead of allowing energy to increase endlessly? The breakthrough came in 1900 from Max Planck, who was studying Blackbody radiation in an effort to preserve classical physics rather than overthrow it. Planck made a bold and unconventional assumption. He proposed that energy exchange between matter and radiation occurs in discrete units rather than continuously. According to his idea, the energy of radiation could only be emitted or absorbed in fixed packets proportional to the frequency of the radiation. This assumption introduced a new fundamental constant, now known as the Planck constant. Although extremely small, this constant had enormous implications. It placed a limit on how energy could be distributed, especially at high frequencies. High-frequency radiation required larger energy packets, making such radiation increasingly unlikely at ordinary temperatures. As a result, the contribution of short wavelengths was naturally suppressed. When Planck used this assumption to derive a new formula for Blackbody radiation, the results matched experimental data perfectly at all wavelengths. The rise, peak, and sharp decline of the radiation curve emerged naturally from the mathematics. The ultraviolet catastrophe disappeared entirely. What classical physics could not fix with any amount of refinement was resolved instantly by changing a single foundational assumption. At the time, Planck did not fully grasp the revolutionary nature of his idea. He viewed energy quantization as a mathematical convenience rather than a statement about physical reality. Nevertheless, the success of his formula could not be ignored. It soon became clear that the classical view of energy as a smooth, continuous quantity was incomplete. The ultraviolet catastrophe thus marked a turning point in the history of physics. It demonstrated that classical theories, no matter how successful, had limits. The failure to explain Blackbody radiation revealed that nature behaves differently at small scales than classical intuition suggested. This realization paved the way for the development of quantum theory, which would soon be expanded by physicists such as Albert Einstein, Niels Bohr, and others. In hindsight, Blackbody radiation and the ultraviolet catastrophe were not merely technical problems, but signals of a deeper revolution. They showed that the foundations of physics needed to be reconsidered and that long-standing assumptions could be challenged by precise experiments. The solution to the ultraviolet catastrophe did more than fix a flaw in theory. It introduced a new way of understanding the universe, one in which energy, matter, and radiation are governed by quantum principles that continue to shape modern science and technology. The birth of the Planck constant marks one of the most profound turning points in the history of physics. It represents the moment when classical ideas about nature quietly but fundamentally broke down, giving way to a new framework that would later become quantum theory. The Planck constant did not emerge from a grand philosophical vision or an attempt to revolutionize science. Instead, it was born out of a stubborn experimental problem and the intellectual honesty of a physicist determined to reconcile theory with reality. At the end of the 19th century, physics was dominated by classical concepts. Energy was assumed to be continuous, meaning it could vary smoothly without restriction. This idea worked extraordinarily well for describing motion, heat, and electromagnetic phenomena on everyday scales. However, Blackbody radiation posed a serious challenge. Experiments showed that the distribution of radiation emitted by heated objects followed a precise pattern that classical physics could not explain, especially at short wavelengths. Every classical attempt to describe this phenomenon led to the ultraviolet catastrophe, a prediction of infinite energy emission that clearly contradicted observations. Max Planck entered this problem not as a revolutionary, but as a conservative physicist. He deeply believed in the validity of classical physics and initially viewed the experimental discrepancies as temporary failures of existing models. His goal was to derive a formula that matched experimental data using established principles of thermodynamics and electromagnetism. When repeated efforts failed, Planck faced a difficult choice: abandon the data or question a foundational assumption of classical theory. In 1900, Planck took what he later described as an act of desperation. He proposed that energy exchange between matter and electromagnetic radiation does not occur continuously, but in discrete amounts. Specifically, he suggested that the energy of oscillators in the walls of a blackbody cavity could only take on certain values proportional to the frequency of radiation. This proportionality required the introduction of a new constant of nature, a number that linked energy to frequency. This constant, now known as the Planck constant, appeared in the simple relation that energy equals the constant multiplied by frequency. At first glance, this equation seemed harmless and purely mathematical, yet it carried revolutionary implications. It implied that energy comes in indivisible units, later called quanta, and that these units become larger as frequency increases. High-frequency radiation therefore required larger energy jumps, making it less likely to occur at ordinary temperatures. The numerical value of the Planck constant is extremely small, which explains why quantum effects were not noticed in everyday experiences. On macroscopic scales, energy exchanges involve enormous numbers of quanta, making energy appear continuous. However, at atomic and subatomic scales, the discreteness imposed by the Planck constant becomes unavoidable and dominant. What made the birth of the Planck constant so remarkable was its immediate success. When Planck incorporated this constant into his radiation formula, the results matched experimental data perfectly across all wavelengths and temperatures. The sharp decline of radiation at high frequencies emerged naturally, and the ultraviolet catastrophe vanished. For the first time, theory and experiment were in complete agreement. Despite this success, Planck himself was uneasy. He did not believe that energy quantization reflected physical reality. Instead, he regarded the constant as a formal device, a mathematical trick necessary to obtain the correct result. He hoped that a deeper classical explanation would eventually be found, allowing the constant to be eliminated. In this sense, the Planck constant was born quietly, without fanfare or recognition of its true significance. The true meaning of the Planck constant began to emerge when other physicists took it seriously. In 1905, Albert Einstein applied the idea of quantized energy to light itself, proposing that electromagnetic radiation behaves as discrete particles, now called photons. Einstein used the Planck constant to explain the photoelectric effect, showing that light can eject electrons from metal surfaces only if its frequency exceeds a certain threshold. This explanation could not be achieved without treating energy as quantized. As quantum ideas spread, the Planck constant became a central feature of the emerging theory. Niels Bohr used it to describe the allowed energy levels of electrons in atoms, explaining why atoms emit light at specific wavelengths. Later developments in quantum mechanics showed that the Planck constant governs the scale at which quantum effects dominate, influencing uncertainty, wave-particle duality, and the structure of matter itself. The Planck constant also introduced a new way of thinking about nature. It established a fundamental limit to how precisely certain physical quantities can be known or defined. In quantum mechanics, the constant appears in the uncertainty principle, which states that certain pairs of properties cannot both be measured exactly. This was a radical departure from classical determinism and reshaped philosophical ideas about causality and measurement. Over time, the Planck constant came to be recognized as one of the fundamental constants of the universe, alongside the speed of light and the gravitational constant. It defines the boundary between the classical and quantum worlds and sets the scale for atomic and subatomic phenomena. Modern technologies such as lasers, semiconductors, atomic clocks, and quantum computers all rely on principles governed by this constant. In retrospect, the birth of the Planck constant represents a moment when physics was forced to confront the limits of its own assumptions. What began as an attempt to solve a technical problem in thermal radiation became the foundation of a new understanding of reality. The constant itself is a reminder that nature does not always conform to human intuition, and that progress in science often begins with the courage to accept unexpected truths. The Planck constant was not announced as a revolution, yet it quietly transformed physics forever. It marked the first step into the quantum world, revealing that at the deepest level, nature is governed not by smooth continuity, but by discrete, quantized structure. Max Planck's place in the history of science is often associated with the birth of quantum theory, yet his personal attitude toward this revolution is just as important as the theory itself. What makes Planck's contribution unique is not only the originality of his ideas, but also his deep reluctance to abandon classical physics and his unwavering commitment to scientific honesty. He did not seek to overturn established laws or introduce radical concepts. Instead, he followed the evidence wherever it led, even when it contradicted his own beliefs. This combination of caution, integrity, and respect for empirical truth defines Planck's scientific character. Planck was trained in the tradition of 19th-century physics, a tradition rooted in determinism, continuity, and absolute laws. He greatly admired classical thermodynamics and believed it represented universal and unbreakable principles of nature. Unlike some of his contemporaries, Planck was not drawn to speculative or revolutionary thinking. He valued order, logical consistency, and mathematical rigor. To him, the task of physics was not to invent new realities, but to uncover eternal laws that already existed in nature. When the problem of blackbody radiation emerged, Planck did not view it as an opportunity for radical innovation. Instead, he saw it as a technical challenge that classical physics should be able to resolve. He was convinced that the laws of thermodynamics, especially the second law, were absolute. His early work on radiation theory was guided by the belief that any correct explanation must be consistent with classical principles. This mindset explains why Planck struggled for years to derive a radiation formula without abandoning continuity or determinism. As experimental data became increasingly precise, Planck faced a growing dilemma. Measurements of blackbody radiation were reliable and consistent, yet classical theory failed to explain them. Many physicists responded by proposing empirical formulas that fit the data without deep theoretical justification. Planck found this approach unsatisfactory. He believed that physics should not merely describe observations, but explain them through fundamental laws. This belief placed him under intense intellectual pressure, as neither classical theory nor existing alternatives provided a satisfactory solution. Planck's reluctance reached its peak in 1900 when he introduced the idea that energy is exchanged in discrete units. He later described this step as an act of desperation rather than conviction. He did not believe that nature itself was quantized. Instead, he treated quantization as a formal assumption, a mathematical tool that allowed him to derive the correct radiation formula. In his own view, this assumption was provisional and temporary, something to be replaced once a proper classical explanation was found. What reveals Planck's scientific honesty is the fact that he published and defended a result he personally doubted. He did not manipulate data to fit his expectations, nor did he ignore experimental evidence that conflicted with his worldview. Instead, he allowed empirical results to dictate theory, even when doing so forced him to adopt ideas he found deeply uncomfortable. This willingness to place truth above personal belief is one of the clearest examples of integrity in the history of science. Planck's honesty also appears in his reaction to later developments in quantum theory. When Albert Einstein proposed that light itself consists of energy quanta, Planck initially resisted the idea. He accepted quantization in the interaction between matter and radiation, but hesitated to apply it to radiation itself. His skepticism was not stubbornness, but caution. He understood the radical implications of such claims and demanded strong evidence before accepting them. Over time, as experimental support grew, Planck acknowledged the validity of these ideas, even when they moved far beyond his original intentions. Unlike some revolutionary figures, Planck did not attempt to reshape physics according to personal ambition or philosophical preference. He did not exaggerate the significance of his work or claim to have discovered a new worldview. For many years, he continued to hope that quantum ideas would eventually be absorbed into classical theory. His reluctance delayed his own recognition as the founder of quantum theory, yet it also demonstrated his humility and respect for scientific continuity. Planck's scientific honesty extended beyond theory into his broader professional life. He believed deeply in the ethical responsibilities of scientists. For him, science was not merely a career, but a moral pursuit guided by truth and objectivity. This attitude influenced his teaching, his leadership within the scientific community, and his interactions with younger physicists. Even when new generations embraced quantum mechanics enthusiastically, Planck maintained a balanced perspective, encouraging innovation while emphasizing rigor and evidence. The contrast between Planck and later quantum pioneers is striking. Figures like Bohr and Heisenberg openly embraced the philosophical implications of quantum mechanics, challenging classical notions of causality and certainty. Planck, by contrast, remained emotionally attached to classical determinism, yet he never allowed this attachment to distort his judgment. He accepted that nature, not human preference, decides which theories are correct. In hindsight, Planck's reluctance played a crucial role in the credibility of quantum theory. Because he was not inclined toward speculation, his results carried exceptional weight. If even a conservative physicist like Planck was forced to introduce quantization, then the crisis in classical physics must have been genuine. His honesty made the quantum hypothesis harder to dismiss and easier for others to build upon. Max Planck's legacy is therefore not only scientific, but ethical. He demonstrated that true scientific progress does not require enthusiasm for revolution, but commitment to truth. His reluctance shows the emotional cost of abandoning long-held beliefs, while his honesty shows the courage required to do so when evidence demands it. In following the data rather than his desires, Planck exemplified the highest ideals of science and unknowingly laid the foundation for one of the greatest transformations in human understanding. The influence of Max Planck on Albert Einstein, Niels Bohr, and the development of quantum theory represents one of the most important chains of intellectual progress in modern science. Although Planck himself was cautious and reluctant about the implications of his work, the idea he introduced transformed the thinking of an entire generation of physicists. His concept of energy quanta became the foundation upon which Einstein and Bohr built radically new models of light, matter, and atomic structure, ultimately leading to quantum theory as a complete framework. Max Planck's original contribution arose from his attempt to explain Blackbody radiation. By proposing that energy is exchanged in discrete units proportional to frequency, he introduced a fundamental break from classical physics. Even though Planck initially viewed this assumption as a mathematical tool rather than a statement about physical reality, it quietly challenged the classical belief that energy is continuous. This single idea opened a conceptual door that others would walk through far more boldly than Planck himself. Albert Einstein was the first to fully recognize the physical meaning of Planck's proposal. In 1905, Einstein took the idea of energy quanta seriously and applied it directly to light. Classical physics treated light purely as a wave, but Einstein suggested that under certain conditions, light behaves as if it consists of discrete packets of energy. Using Planck's constant, he explained the photoelectric effect, a phenomenon in which light striking a metal surface ejects electrons only if the light's frequency exceeds a specific threshold. Classical wave theory could not explain this behavior, but Einstein's quantum explanation matched experiments perfectly. Einstein's work went beyond Planck's original intent. While Planck had limited quantization to the interaction between matter and radiation, Einstein argued that light itself is quantized. This was a bold and controversial step, and even Planck initially resisted it. However, Einstein's use of the Planck constant demonstrated that quantization was not a mathematical trick, but a real feature of nature. This marked a turning point, as quantum ideas began to move from isolated problems toward a broader theory. Einstein's influence, in turn, inspired other physicists to explore the quantum nature of matter. One of the most significant among them was Niels Bohr. In 1913, Bohr applied quantum ideas to the structure of the atom. Classical physics could not explain why atoms are stable or why they emit light at specific wavelengths. Bohr used the Planck constant to propose that electrons can occupy only certain allowed energy levels within an atom. When an electron jumps between these levels, it emits or absorbs a quantum of energy. Bohr's atomic model was revolutionary. It combined classical concepts, such as electrons orbiting a nucleus, with quantum restrictions imposed by Planck's constant. Although the model was later refined and partially replaced, it successfully explained the spectral lines of hydrogen and provided strong evidence that quantum rules govern atomic behavior. Without Planck's constant, Bohr's model would have been impossible. The influence of Planck on Bohr was not merely technical, but conceptual. The idea that nature allows only certain discrete states challenged classical continuity and forced physicists to rethink the meaning of physical laws. Bohr embraced this challenge more openly than Planck, developing philosophical interpretations of quantum behavior that emphasized limits on classical descriptions. Yet even as Bohr pushed quantum ideas further, the Planck constant remained at the heart of his work. As quantum theory evolved, Planck's constant became a universal feature of the new physics. It appeared in equations describing atomic spectra, radiation, and later the wave-like behavior of particles. The constant defined the scale at which quantum effects become significant and distinguished the microscopic world from the macroscopic one. Einstein and Bohr, despite their later disagreements about the interpretation of quantum mechanics, both relied on Planck's constant as an essential element of their theories. The broader development of quantum theory in the 1920s, including matrix mechanics and wave mechanics, further expanded the influence of Planck's original idea. Physicists such as Werner Heisenberg and Erwin Schrödinger built mathematical frameworks in which the Planck constant played a central role. It governed uncertainty relations, wave-particle duality, and the structure of quantum equations. These developments would not have been possible without the conceptual break initiated by Planck. Ironically, as quantum theory matured, Planck himself became increasingly distant from its more radical interpretations. Einstein famously questioned the completeness of quantum mechanics, while Bohr defended its probabilistic nature. Despite these debates, all sides recognized the foundational role of Planck's contribution. The disagreements were not about whether Planck's constant mattered, but about what it ultimately meant for reality. The influence of Planck on Einstein and Bohr highlights an important pattern in scientific progress. Revolutionary ideas often begin cautiously, introduced by those who do not fully accept their consequences. Others, more willing to challenge tradition, then expand these ideas into complete theories. Planck provided the key, Einstein unlocked the door, and Bohr explored the room beyond it. In the end, Planck's influence extends far beyond individual scientists. By inspiring Einstein and Bohr, he helped create quantum theory, a framework that reshaped physics, chemistry, and technology. From atomic clocks and lasers to semiconductors and modern electronics, the legacy of this intellectual chain is everywhere. What began as a modest attempt to solve a radiation problem became a transformation of human understanding, driven by the shared efforts of Planck, Einstein, Bohr, and the quantum theory they collectively brought into existence. The lasting impact of quantum theory on modern science and technology is one of the most far-reaching transformations in human history. What began as an attempt to solve abstract problems in theoretical physics has grown into a foundation that supports much of the modern world. The ideas introduced at the beginning of the 20th century, especially those rooted in Max Planck's work, reshaped how scientists understand nature at its most fundamental level and enabled technologies that define contemporary life. In science, the most profound impact of quantum theory lies in its revision of the basic concepts of matter and energy. Classical physics viewed the universe as continuous, predictable, and deterministic. Quantum theory replaced this picture with one in which energy comes in discrete units, particles can behave like waves, and probabilities play a central role. This new framework allowed scientists to explain phenomena that classical physics could not, such as atomic stability, spectral lines, and the behavior of electrons in atoms. Without quantum theory, modern physics, chemistry, and materials science would lack their theoretical foundation. One of the most significant scientific impacts is in atomic and molecular physics. Quantum theory explains why atoms have specific sizes, why electrons occupy distinct energy levels, and why atoms emit or absorb light at precise wavelengths. These insights made it possible to understand chemical bonding, molecular structure, and reaction mechanisms. Chemistry was transformed from a largely empirical discipline into a predictive science grounded in quantum principles. Modern fields such as physical chemistry, quantum chemistry, and spectroscopy all depend directly on quantum theory. In solid-state physics, quantum ideas explain how electrons move through solids and why materials behave as conductors, semiconductors, or insulators. This understanding is essential for modern electronics. The ability to control electron behavior in materials led directly to the invention of the transistor in the mid-20th century. The transistor replaced bulky vacuum tubes and made it possible to build smaller, faster, and more reliable electronic devices. Every computer, smartphone, and digital system today relies on quantum principles operating silently at the microscopic level. Semiconductor technology, which underpins modern computing and communication, is a direct product of quantum theory. Devices such as diodes, integrated circuits, and microprocessors function because electrons occupy quantum states within materials. Engineers design these systems using quantum-based models, even if the final devices appear classical in operation. The exponential growth of computing power over the past decades would have been impossible without this quantum foundation. Quantum theory has also had a profound impact on optics and photonics. Lasers, one of the most important technological inventions of the 20th century, rely on quantum transitions between energy levels in atoms or solids. Lasers are now used in medicine, industry, telecommunications, entertainment, and scientific research. Fiber optic communication, which carries vast amounts of information across the globe, depends on quantum principles governing light-matter interaction. The modern Internet itself rests partly on ideas that originated in early quantum theory. In medicine, the influence of quantum science is both direct and indirect. Medical imaging technologies such as magnetic resonance imaging rely on quantum properties of atomic nuclei. Diagnostic tools that use spectroscopy to analyze tissues or blood samples depend on quantum interactions between light and matter. Even pharmaceutical development benefits from quantum chemistry, which helps researchers understand molecular interactions and design effective drugs with greater precision. Quantum theory has also reshaped our understanding of energy and materials. Modern solar cells operate based on quantum effects in semiconductors, converting light into electricity with increasing efficiency. Light-emitting diodes used in energy, efficient lighting, and displays rely on quantum transitions in materials. Advances in battery technology, superconductors, and nanomaterials all depend on quantum-based models of matter. In fundamental science, quantum theory continues to drive progress. Particle physics, which explores the most basic constituents of matter, is built entirely on quantum principles. The standard model of particle physics uses quantum field theory to describe forces and particles with extraordinary accuracy. Experiments at large facilities rely on quantum predictions to guide their design and interpretation. Without quantum theory, modern cosmology and our understanding of the early universe would be incomplete. Perhaps the most exciting modern development is the emergence of quantum technologies. Quantum computing aims to use quantum superposition and entanglement to perform calculations that would be impossible for classical computers. Although still in early stages, this field promises breakthroughs in cryptography, materials discovery, and complex simulations. Quantum communication offers new methods of secure information transfer based on fundamental laws of physics rather than computational difficulty. Beyond practical applications, the lasting impact of quantum theory includes a profound shift in how humanity views reality. It challenged classical notions of certainty, determinism, and objective measurement. While these philosophical implications remain debated, they have influenced scientific thinking across disciplines. Quantum theory taught scientists that nature may not conform to everyday intuition, and that mathematical structure and experimental evidence must guide understanding, even when results seem counterintuitive. Importantly, the impact of quantum theory did not arise overnight. It unfolded gradually as abstract ideas were tested, refined, and applied. Many early contributors, including Max Planck, could not have predicted the technological consequences of their work. Yet their commitment to understanding nature at a fundamental level made these advances possible. Today, the influence of quantum theory is so deeply embedded in modern life that it often goes unnoticed. From the devices people use daily to the scientific tools that expand human knowledge, quantum principles operate in the background. The lasting impact is not limited to specific inventions, but lies in the creation of a new framework for understanding and shaping the physical world. In conclusion, the legacy of quantum theory on modern science and technology is vast, enduring, and still evolving. It transformed fundamental science, enabled revolutionary technologies, and reshaped humanity's relationship with nature. What began as a solution to a theoretical problem became one of the most powerful intellectual achievements in history, continuing to influence the present and shape the future.